Okay, let's see how to analyze a series circuit. So we learned that in electronics, people understand how to deal with circuits and how to figure out how to get the power across them. So let's go ahead. I'm going to put the battery up the top. It does not matter where these resistors are. Beautiful resistors, aren't they? Okay, so we're going to have a voltage across this battery. We'll have, this is the small side, so that's the negative side. And that means this is the positive side. If I throw a positive right here, I know it goes away from the other positive, so conventional current's going to go counterclockwise in this case. And I'm going to erase that so it doesn't muddy up my waters here. And then we have resistors. So this, let's go back a little bit for a second. Let's call this resistor 1, resistor 2, and resistor 3. Now, as you can see, since there is only one path, if there's only one path, between resistors, they are connected in series. Therefore, the current is the same for each resistor. Okay, so that's important to know. Number one. Now, we also know something else, that the voltage in, I don't want to say voltage, I want to say the energy. The energy in the system equals the energy used up. Okay, so with those two things, let's go ahead and see what we can do. We know that the current flow is the same through every single thing. So the current from the battery, I like to use the current through the battery, it's a big capital I. Current through the first one, the current through the second one, and the current through the third one are all exactly the same. It's conservation of charge that we looked at earlier. The energy in the system, in, is the voltage. Let's go ahead and see what I've got here. And let's see, so the total energy from the bulb equals, I'm going to go ahead and put a lowercase I here, and a lowercase I here. So those, the current through with 1 times the resistance, remember this is V equals IR, so this is a voltage drop across each resistor. If you add them all up, you end up getting the voltage from the battery. Now, I worked so hard at making sure all these I's were different, but really they're exactly the same. So I could actually rewrite this as I in front of this one, just a big capital I, they're all the exact same current. Well, I'm going to use some Algebra 1 skills. I'm going to combine all those I's together. I'm going to factor out the current, and I get the fact that you can just add all those resistors together first. So, remember we were talking about equivalent resistance in class. I could just say I times the equivalent resistance. There we go. And what is the equivalent resistance? Is the sum of all of the resistors. As long as it's in series, we've just proven that. You guys proved that algebraically too. That's pretty cool. There we go. So let's go ahead and put another thing that we know then. the equivalent resistance in a series circuit is the sum of the resistances. There we go. Looks like we could also, I guess we pretty much say the voltage drop for each of them is equal to the voltage drop of the battery. Let's go ahead and spell resistances correctly. There we go. I'm going to go ahead and do the next video, and we're going to talk about how to actually figure out what to do in that circuit.